Finally, we're going to get a little bit of practice in computing antiderivatives. So we'll have our first encounter with actually computing the antiderivative of a given function. And we're going to start off by my list of 5 basic antiderivatives, or if you want to call it that, 5 basic integrals. So this is the list of 5 basic antiderivatives, or 5 basic integrals. So the first one, we have the integral of x to the n dx. Okay, well, let's put on our thinking caps. We saw the derivative of x to the n. The exponent came down, so the n came down, and then we subtracted 1 from the exponent. So to compute the integral of x to the n, we basically do the steps in reverse. So first we add 1 to the exponent instead of subtract 1. So instead of subtracting 1, I add 1. And then second, instead of multiplying by the new exponent, I divide by the new exponent. So I get x to the n plus 1 over n plus 1 and then plus c. So the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. Now, when you think about these backwards, and you have to kind of think backwards to go from a function to its antiderivative, it's always useful to go back and check your work by thinking forwards, because you have much more practice as of now thinking about taking derivatives. So then take a step back and say, okay, what's the derivative of this? Well, the derivative of this I can do almost in my sleep, right? So I have x to the n plus 1. The n plus 1 comes down up front. And notice that when I multiply by n plus 1, it's going to cancel out with what's in the denominator. And then I subtract 1 from the exponent, so the x to the n plus 1 turns into x to the n. So the derivative of this really is just x to the n. Now and this is for n not equal to minus 1. So if we have n is equal to minus 1, we have a problem, because n plus 1 would be 0. We would have x to the 0 divided by 0. So let's do that one as a separate rule. 1 over x dx. Well, we know what this integral is. It's the ln of x plus c, because the derivative of ln of x is 1 over x. So if we want to integrate 1 over x, we get ln of x. So next we have sine of x. Now the integral of sine of x is not cosine. The derivative of sine is cosine. So how do we find the integral of sine? Well, it's probably going to be something related to cosine. And we can always think backwards. The derivative of cosine is minus sine, but I don't have a minus sign here, so I better put it there. So I get minus cosine of x plus c. Right? The derivative of minus cosine of x is the minus here, and the times the derivative of cosine. The derivative of cosine is negative sine of x. The two negatives cancel and we just get sine of x. And then the integral of cosine of x is going to be plus sine of x, because the derivative of sine is cosine, and then plus c. And then finally, the integral of e to the x dx is equal to, you guessed it, e to the x plus c. Right. So these are the 5 basic antiderivatives. In addition to these, we have the same linearity rules that we saw when we studied derivatives. So in addition, we have these linearity rules. So in other words, the integral of f of x plus g of x is equal to the integral of f of x and then plus the integral of g of x. Now this is as long as these two individual integrals exist and are well defined. And then also the integral of a constant times f of x is just equal to a constant times the integral of f of x. And basically these stem exactly from the linearity rules for differentiation, because this says that, well, what function has the derivative of f of x plus g of x? Well, if I can answer that for f of x, and I can answer that for g of x, and I need a dx over here, don't want to leave the integral sign without the dx. The dx basically closes the integral sign. If I can find the antiderivative for f of x and I can find the antiderivative for g of x, I add them together and I get the antiderivative for f of x plus g of x. Basically works like that. One thing, and of course, this kind of falls from these rules, but I'm going to point something out with it. The integral of f of x minus g of x is going to equal the integral of f of x minus the integral of g of x. And you can get this just by combining our two main ones up here. The reason I'm writing it like this is that when you find these integrals here, you're going to get a plus c for both of them, and there's a minus sign. And it's going to be tempting that you're going to want to subtract the two plus c's. Suppose you have an antiderivative for little f and little g. So for example, capital F of x plus c, so that's this integral, and then minus capital G of x plus c, which would be this integral. And you say, c minus c is 0, so this integral is just capital F of x minus capital G of x. Nice try, but there's still a plus c there. And the reason is that this c that you get for doing the integral of f is different than the c you get for doing the integral of g. So you don't want to cancel them out because they can potentially be different plus c's. So when you have multiple plus c's like this, you can combine them and lump them together into just one final plus c at the end. So that's just a little word of warning with respect to that.